Okay, ladies and gentlemen, so today I want to go over, well, I want to expand actually upon what we've been doing with basic circuits. If you remember, we had a couple of videos explaining all the basic rules about how circuit elements go into a circuit diagram, how we then can use the fact that we can choose a starting point to evaluate a circuit, and then from that starting point, we go around closed loops. And then when we go around closed loops, we have these rules that said, if you're going with the current for a resistor against the current for a resistor, yada, 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 that we could build the fact that delta V, the change in potential from a point A to a point A or point B to a point B around any closed loop has got to be 0. So that we've seen was very powerful for solving circuits with different unknowns and also powerful for circuits with different loops, okay? But so far right now, all of the ones that we solved were what I would consider basic circuits. And what a basic circuit means is that for every loop that you choose, you basically only have one unknown in that loop, and therefore you can solve its equation for whatever that unknown is, right? Now, we've seen a problem in the previous video when we did some more slightly advanced problem solving that certain loops did have two unknowns, but if we just skipped them for the moment and went down, or we used the junction rule, right, we always had a way of getting out, at least in the ones that we've done, of still only solving one equation and one unknown. It's inevitable, though, that certain combinations of what is given versus what you're looking for are going to lead you to the case where each loop itself might have multiple unknowns, and therefore the only way that we can solve those is by solving one equation for one variable and plugging it into another, and perhaps doing that up to 3 times. Right, solving simultaneous equations. The physics of what we're about to do is not going to change. It's the exact same physics that we've been doing. It's the exact same rules that we've been using. However, what is going to be stepped up here is the algebra. So I want to go through 2 problems today that allow us to look at, we're going to use the same physics to generate the same type of equations. However, the downside is that those equations then are going to be more complicated, and we're going to have to work through the algebra to solve them out. So let's do it. Okay, so this is the first, slightly complicated circuit that I want to solve. We have a situation very similar to what we had a few times now, namely 3 branches: top branch, middle branch, bottom branch, okay? We have 2 resistors on the top branch and a battery, 2 resistors on the middle branch and a battery, and only a resistor in the bottom branch, okay? We know all of those voltages and all of those resistances. The only unknown here, the only unknown are all 3 currents, okay? So we need to find all 3 currents, I top, I mid, or I bottom, or I'm just gonna rename that to I1 for the top, I2 for the middle, and I3 for the bottom, okay? And those are the things that we want to find. If that's the case, ladies and gentlemen, the first thing that we're gonna do before we can start building our equations is we have to assume a direction for these, okay? So I don't know which way they're gonna go, so why not? I'm gonna choose that they hopefully go the way that I would want them, right? That namely the currents flow out of the batteries, but let's see if that's actually the case, if we get a negative sign for one of them or anything like this, okay? Next thing, now that we've assumed a direction, again, for I1 in the top, I2 in the bottom, and I3 in the, I2 in the middle and I3 in the bottom, we can now do our loops. How many loops do I see? 3. Top loop, bottom loop, overall outside loop. But we also know that we get one for free, right? We get one other given for free, and that's the fact that at any junction, what flows in has to be equal to what flows out. So what does my junction rule then tell me in this case here? It says that I1 plus I2 is equal to I3 as I have drawn it. So we're going to keep that in the back of our brains in case we can use it later on down the road in this problem. Okay, so I'm going to start from the top left like I always do, and I'm going to do the top loop first, and I'm going to go in this direction. Starting there, I come down. The first thing I encounter is a resistor R3, but I'm going against it, so I pick up an I2 R3. I go against the battery E2. I pick up an I2 R4. I lose an I1 R2. I pick up an E1 and I lose an I1 R1. okay? And then I'm back home, so that whole thing is equal to 0. 1, 2, 3, 4, 5, 6 elements, I'm sorry, 6 numbers in total, because we expect that for one of those terms for each of those elements, okay? Since I already know that each one of these has 2 unknowns, right? If you take a look, I2 is not known, I1 is not known, okay? I want to just plug in the rest of the values. That way I see what this equation looks like without units at its bare bones. R3, etc. We plug in all these values, okay? And what I get is I2 minus 5 plus 4I2 minus 3I1 plus 10 minus 2I1 is equal to 0. That's plugging in all of the resistances. Now, grouping all of our terms together, bringing all of our I1s with I1s and I2s with I2s, I see that this is 5 I2s in total minus 5 I1s plus 5 is equal to 0. Or another way of saying that is that I can move the 5 over to the other side and divide by 5, and that I2 minus I1 is equal to -1. And we pause. Again, that's as simple as we can get that equation, and we see that it has 2 unknowns. But it is a combination of I1 and I2. This is another combination of I1 and I2, but that brings I3 into the picture, which we don't have yet. So let's see if we can keep going. We've only exhausted one loop. We still got 2 more loops that we can use, okay? So that's what I want to use next. Let's do the bottom loop. Okay, and I'm gonna do that one in a different color. Let's do that one in purple. So in the bottom loop, again, doing the exact same direction. The first thing I encounter is the resistor in the direction of current. And so that's a minus I3, and I called that R5, I believe. Minus, then along the bottom, I go with the current, minus I2 across R4. I pick up the battery E2, and I lose I2 R3, and I'm back home. So again, getting this as simple as possible, plugging in the resistances, what I see is that this is minus 10 I3 minus 5 I2 plus 5 is equal to 0. Again, just moving the 5 over and dividing both sides by that. And let me just make sure that I have my signs correct here. Minus, minus, plus. Yes, that is good. Okay, so dividing out the 5, what I see is a minus 2 I3 minus I2 plus 1 is equal to 0. Okay, and so from that, I can rearrange this and say that, well, 2I3 plus I2 is the same as 1. Okay, well, what I'm going to do is I'm going to stop right there, because it's my argument to you algebraically that we now don't even need the outside loop, okay? What is the outside loop going to do for us? It's going to mix the equation with I3 and I1, because I1 is in the top and I3 is in the bottom. But how many equations do I have now? I have 1 in green, 1 in purple, and my junction equation up here in red. I have 3 equations for 3 unknowns. So mathematically speaking, that should be enough to satiate the system, okay? But again, all that we did up to this point is do the same physics that we've already done. Now we pause, and now we're gonna have to do the algebraic mess of untangling these 3, okay? So let me, again, the bottom equation has an I2 and an I3. The middle equation has an I2 and an I1. The top equation has an I1, an I2, and an I3. 3 equations, 3 unknowns, okay? So what I want to do is I want to take this one in red. You could do this in any order that you want, right? This is just what I see looks the best, right? That this tells me that I3 can be substituted by I1 plus I2. So I'm going to take that red one and shove it into this one for where there's an I3. And I'll do that substitution again in red to see it coming in. I replace I3 with an I1 plus I2, and then whatever's left over is still there. I now distribute that out, okay? And so I'll do all the new stuff now in black. 2I1 plus 2I2 plus I2 is equal to 1, okay? Another way of saying that is 2I1 plus 3 I2 is equal to 1. Okay, and we pause. Okay, because now what we have successfully done is we've gotten this thing in terms of both I1 and I2. Okay, so we're still got to do a little bit more in order for us to get this to come out. So we now can use what we know from green, and let's just make green a little bit more straightforward. Let's just solve green for your favorite one. I'm going to solve it for I2. That's going to be a -1 plus I1, and I'm going to take that and shove it down here. And again, if we do this right, we then should be left with only one unknown. That then leaves us with, and I'll do the substitution in green, 2I1 plus 3, and I replace that with green, -1 plus I1. -1 plus I1 is equal to 1. Oh, technically speaking, that's not green. Okay, now if we take a look, there is one and only one unknown, and that one unknown is I1. So now I'm going to solve this for I1. Okay, being careful with our algebra, 2I1, let's distribute this out. -3 plus 3I1 is equal to 1. Okay, so we move the 3 over to the other side, which gives us 4, and we get 5I1 is equal to 4, or another way of saying that is that I1 is 4/5 of an amp. And so we did it. We have our first current I1, and we know that since I1 is related to I2 and I3, once we have I1, we can back substitute all of these to get the other two. Let's do that. If that is I1, which is 4/5 of an amp, well, we can right away then see that I2, we said, was the substitution in green. I2, remember, was -1 plus I1, which is the same as -1 plus 4/5, which is also known as -5/5 plus 4/5, which is -1/5. And what do you know? We got a negative sign. So again, what does this mean? It means that the value of the current is correct, right? It's 1/5 amp, but we just drew its direction wrong. But we don't replace anything, right? We don't go back and redraw or restart the whole system over, because remember, everything is consistent to the way that we drew it. So we have the value now for I2, and then we know back where we started with our junction rule that what flowed in, or what we had assumed flowed in, I1 plus I2 was I3. We take those values as given now, 4/5 amps plus a -1/5 amp is equal to 3/5 of an amp, and that is our current I3. It still obeys our I1 plus I2 is equal to I3. Now let's pause and go back and say, well, what if we had drawn it properly? If we had drawn it properly, that means that I2 would have actually been going in this direction here. And if I2 was going in that direction, then what would our junction rule have actually been? It would have been I1 flowed in, I2 plus I3 flowed out, except now we would have had the direction right, which would have not given us that negative sign in the first place when we solved it, but the values would have been the same. And what do you know? I2 being 1/5 and I3 being 3/5 would have still given us a 4/5 amp, no matter how we chose to do it. Okay? Let me summarize here. Yeah. All right. Up to this point, boom, that was the physics. Everything else was algebra. Okay? Again, we used our rules to get this to come out. Okay? And then we just had to play a very lengthy algebra game. Let's do another one to make sure that we have even more fun with this. This is ones that I really enjoy. Okay? Lots of ways that we can solve this one, but I want to do the same thing by just identifying loops and solving loops, 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 and seeing how they plug in. We have all the batteries. We have all the resistances. So we could resort back to our old techniques of, finding the total resistance, finding the total current, and then seeing how the current breaks off. But we see there's lots of breaks here. So I don't know if that's going to necessarily be any easier. But it's always good for us to know that there's more than one way to solve something. So let's just use these same rules that we've been doing over and over again, okay? So I'm gonna call this, I meant to call this I1, and we do acknowledge here that I1 is the same as I total, right? Because it's all the current that leaves the battery, and there's only one battery, okay? Nonetheless, let's start doing loops, okay? For this problem, okay, in each one of them, I'm gonna start from the top left of a given loop, okay? But just because all the currents are flowing to the right and down, okay, I'm gonna do each one of my loops this time in a clockwise fashion, just because it'll just make things much, much easier for us, okay? Or just more straightforward, okay? So how many loops do I see? I see 4. Left, middle, right, and overall outer loop. And I think we're probably gonna need most of them. So let's just start cranking through, okay? If that's the case, let's start with the leftmost loop and see what equation that generates for us. So starting from the top left point and going across, I lose an I1 R1. Then I lose an I2 R2. And then I come back and I pick up the battery equals 0. And ladies and gentlemen, just like how I started this video saying that there are some circuits that no matter how hard we try, we're not going to have, or we're going to generate equations with 2 unknowns. Here we go. What are the 2 unknowns here? Let's just underline them, I1 and I2. So we can't do anything about that yet. But what can we do? We can identify our 2 junction rules here, yes? Namely that I1 flows into the junction and outflows I2 plus I3. But there's another junction which says that I3 flows in and I4 plus I5 flows out. So we got a lot to solve for here still. Left one gave us an equation in terms of 1 and 2. Let's go to the next one. Middle loop, starting from that point. The first thing I do is I lose an I4 R3. Then I come back around and I pick up an I2 R2 and I'm back home, so that equals 0. Okay? In order for me to probably make my life a little bit easier, let me do exactly what I did last time and get these equations down into their simplest fashion, okay? So I'm just gonna actually select this and just move it ever so slightly down a bit. That way I can actually plug in this other one up here in black. Plugging in the R1, this is really a minus 3 I1. Plugging in R2 as 4 minus 4 R2 plus 12 is equal to 0. Just so we see, again, what the simplest version of these equations are that we're dealing with here. Plugging in I4 and, I'm sorry, R3 and R2, then we see that this is a minus, and let's keep that one in green. This is a minus, R3 is 48 I4, and you know what, why not just move it over to the other side, right? 48 I4 is equal to I2 times R2, which is 4 I2. And another way of saying that, right, is we can just take 4 and divide it by 48, but we could just leave it like that for the moment, okay? Right, so it's up to you. Either way, let's keep going. This was the middle loop, okay? Again, take a look at what's happening. An equation with I1 and I2, sorry. An equation with I2 and I4, so we gotta keep going. Let's go to the right loop. Let's do that one in purple. Okay, doing the right loop, again, starting from this point. The first thing I encounter is a minus I4, I'm sorry, I5, R4, but then I pick up an I4, R3, and I'm back home. So once again now, just looking at this in its simplest possible way, R3 was that obnoxious 48 ohm resistor again times I4 is equal to R4 is 16 I5, okay? Another equation that puts I4 and I5 on the same page. But let's pause for a moment. How many equations do we actually have right now? We technically have 5. And how many unknowns do we have? 5 unknowns. So we could choose to pause here, but while we're at it, let's just do the overall outer loop. And I'm going to do that in a slightly different orangey color here. Okay, the outer loop, again, starting from the top, okay, and going all the way to the right, I lose an I1, R1, I lose an R4, I5, and I pick up the battery and I'm back home. Okay, so plugging those values back in, R1 is 3, the battery is 12, so this is a minus 3I1 minus 12, I believe, sorry, 16, I5 plus 12 is equal to 0. And now we have an equation that relates I1 and I5. We have everything down to about as straightforward as we could possibly want it. So now all the physics is done. Now we're just back in algebra land, and we got to be patient and just plow through the algebra. So let's just crunch through that algebra, okay? We can see that another way of saying this is I2 is equal to 12I4, and I5 is 3I4. So if that's the case, let's go back to our junction equations, okay, which says that I3 is I4 plus I5. And I'm going to do all the rest of this now back in black. So if I3 then is I4 plus I5, but I now know that I5 is 3I4s, I can make that substitution. And another way of saying that is that I3 is just 4 I4s. Okay? Now, if I3 is 4 I4s, we also know that I1 was equal to I2 plus I3, our other junction equation. But now, we can say, though, this is I2, but I3 is 4 I4s. And it looks like we're just mixing ourselves up, but remember, I2 we could plug in because it's 12 I4s. So this is 12 I4s plus 4 more I4s, namely I1 is also known as 16 I4s. Wow, so we're getting almost everything down to an I4. Now, if that's I1 and that's and we have everything in terms of I4, now we can pick the only equations left that we didn't use, either the one for the outer loop or the one for the top loop, and finish the job. I'm going to use the one for the top loop. The top loop says that minus 3 times I1, which we just said was a 16 I4, minus 4 I2s, and I2s we said were 12 I4s, plus 12 is equal to 0. And we see here that there is one and only one unknown here, and that unknown is I4. Okay, so just to be careful with my algebra here, I'm going to make sure that I use a calculator. 3 times 16 gives me 48 I4s. 4 times 12 also gives me a negative 48 I4s, plus 12 is equal to 0. 48 plus 48 gives me 96 I4s in general, and that is an overall negative 96 I4s is equal to negative 12. And so therefore 12 divided by 96 does return us a positive current of 0.1 I4 being 0.125 amps. So if we know I4 is 0.124 amps, well, let's go back and get all of the rest then, because I1 we said was 16 of them, which is 2 amps. We know that I2 was 12 of them. I3, which did not appear in any equation, but we now know it, it's I1 plus, I'm sorry, I3 we said was 4 I4s. I'm sorry, it didn't appear in any loops, but here it is here, okay? Because we got it from the junction rule. So I3 was 4 of those I4s, 0.5 amps. I4, well, that's the one that we found, which lastly leaves us with I5, which if we come back over to here, we said that I5 was 3 of them. So this is 0.375 amps. We can do our gut check on all of these. And what we see, remember, is that I1 should equal I2 plus I3, and it certainly does. And I3 has to be equal to I4 plus I5, and it certainly does. The world is a happy place. Okay? What's the other way that we could have attacked this? We probably could have got the total current, 2 amps, right? Or the current that went through the first one that came out of the battery, by first looking at this and saying this is a network of resistors with R1 in series with the parallel combination R2, 3, 4, and 1 over R2, 3, 4 is equal to 1 over R plus R2 plus 1 over R3 plus 1 over R4. Solve for that, get that net resistance. Once we get the net resistance, since we have the net voltage, find the net current. But that would only work for us to get that first current, and then we'd have to do the fact that the current splits at each one of these, and then we have to figure out how much potential difference we pay. Either way, we'd be solving 5 equations at least to get this done, which is exactly what we did here. I highly encourage you to try it that way. That way you can see that either way we want to get to the same result, it will actually get us down to the same result. So, ladies and gentlemen, a couple of takeaways here. The physics has not changed. What we're doing in the physics really hasn't changed. We're applying those same exact rules no matter how complicated we make that circuit, okay? What does change is that with it comes a boatload more algebra that we gotta be prepared for, okay? If anything in this video was confusing, please slow it down. Please go through it step by step, because these are the types of problems that you'll be expected to do in the extremum case, but also for the upcoming homework. As always, ladies and gentlemen, if you have any questions, comments, complaints, or concerns, please don't hesitate to reach out to me. After this video, we're going to do another video, which will be a much shorter one, which ties up a couple of loose ends about circuits before we move on to bigger and better things. Until then, I hope that you enjoyed this video, and I hope that you have a fantastic weekend.